to the one of you that sent me that. But before I get going with the multiple expansion, were there things about separation of variables that you wanted me to maybe refresh or like explain in the detail, or can I kind of let you digest it? How's it going with separation of variables? It's tough, right? It's tough. However, you know, the general Platonic idea, the kind of thing high up in the air of the approach, I hope that has been like communicated. Yeah, question.
So the part from calculating the CN variable.
Yeah. Are you the one who emailed me? Or
I was not.
No, okay.
The part was a little bit weird because we use a part of the equation that we multiply it the same thing.
So what were we doing? Let's just go to exactly what you mean. Maybe maybe the one with the example that we were doing with the Cartesian, perhaps perhaps here.
This one's a little bit different than the one in the website.
So it's the one about the Cartesian coordinates. So yeah, so this is the fulfillment of the last boundary condition that we had, which was, you remember, we had these two semi-infinite plates, and on one end there was a little strip that was held at a potential phi 0 of y, which was just stated as a function but not explicited as a function. So, you know, yeah. So getting back to your question.
Yeah, I'm not sure. I think that it myself. I don't know how to.
So let me try to answer a question which I think many people might have. So, and then maybe it happens to be the one that you have here. So the point is that we are dealing with complete sets of basis functions to fit. And when we write the general solution to the Laplace equation, we write it by the principle of superposition as a linear combination of lots of different basis solutions combined with each other with little numerical coefficients, saying, you know, 1% of that one, 3% of that one, etc., etc., etc. Okay? So these 1%, 3%, these are the Cn that we have here. Okay, because our general solution is, we had written it just in the previous part here, our general solution, which is this form here, phi for all x and y within the region that we had. We remember that there's no z dependence by symmetry. The x and y dependence is given by this particular summation of the basis function. So each of these basis functions, e to the minus knx sine kny, fulfills Laplace, okay? But of course not yet the boundary conditions, because we haven't done that yet. But we know that the solution that fulfills the boundary conditions has to be composed of a summation of all these independent basis functions, correctly cooked together so that the boundary conditions are satisfied. Okay? So the task of fulfilling the last boundary condition that we had here is mathematically simply the task of computing each and every one of these Cn coefficients. Okay? And in order to do that, we use a kind of reverse engineering trick. Because we know that our solution is a summation of all these basis functions, we want to chop up this particular thing here in order to fish out only one of the Cn's. If you're mathematically minded, one way you can view this here is like, you know, a big like vector multiplying another vector. And what we're trying to do is determine one of the vectors. So we just want to kind of extract the components in here. So how do we do this? We apply an operation on the left and right of the equation, which will invert the summation if you want. So what it does here, I take this equation here literally, and I multiply it by a function sine of kn prime y for my choice of n prime. And I do that on both sides. And then on both sides, I integrate over y, over the chosen interval. And because I am dealing with these orthogonal functions, this picks out for me only one non-zero term, which is the one where in the summation here over n, the index happens to coincide with my chosen n prime. Okay? So this is what I'm doing here. I am doing the left-hand side of this. But when I do the left-hand side, the point is that when I perform the integral, due to the orthogonality of the functions, I pick up a Kronecker delta. That n in the sum here has to be equal to my chosen n prime for each n prime that I will put in this machine, one after the other. Therefore, I can now perform the sum over n because I've got my Kronecker delta. And the left-hand side now evaluates to something which is what I want, which is the coefficient c, but at my chosen index n prime. Okay? So that's the left-hand side. But the right-hand side, I just do exactly the same operations, and I am left with an integral of my original source function phi 0 of y, which I don't know, but which I presume given, and a totally well-defined integral of this weighing function with integration over this interval. So this is computable.
I have one last question. So the integral, how do you determine it? Or is it dependent on the function that you have? Because the base function that you have was also with the sign, or you can use the sign, or it is always the same?
No, it's so the question is, what determines these functions here? So here we are already a bit deeper in the solution of our problems. We have already fulfilled other boundary conditions. If we go back, before we do anything with any boundary condition, what we had was, after invoking separation of variables, a completely general solution for both the x part and the y part. So at this stage, we have not specified anything. However, we have written the most general solution that there is. So in general, it's not a sine function. It's a combination between a sine and a cosine. But that depends on the other boundary conditions.
Right.
Yes. So our complete set of orthogonal functions in the y direction is sine and cos for all values of these k's that we found. However, the cos is not acceptable because it doesn't fit the boundary conditions of having the two plates at zero potential. Okay, but if I did have a different boundary condition, I would have a cos, but then I would do integrals. So in completely general boundary conditions, I would need to compute the Cn and the Dn. In order to compute the Cn, I do exactly the same as I've got here. In order to compute the Dn, I just use cos Kn Kn prime x, and I integrate over this. Okay? So this is the idea. We use orthogonality of the functions to invert this summation here. And we find all the coefficients one after the other. So I've done it now for a particular n prime, but of course I can do this for any chosen n prime. That is, I need to do it one after the other. Okay? So each of these coefficients is given by this integral. And here from this line to this line, I am not doing anything more brutal than changing the index label. Instead of n prime, I just say, well, let me just write n. Okay, which is the same thing because it's just a thing. Okay, so that's the logic. Write general solution in terms of a linear combination of mutually orthogonal functions. Okay, and then use your boundary conditions in order to compute the coefficients in the linear combination of these orthogonal functions that you have to obtain the solution. Okay, so this should really remind you very much of Fourier analysis, Fourier series. That's what you do in a Fourier series. You compute Fourier coefficients. And how do you compute a Fourier coefficient? You take your basis function, you multiply it by one of the Fourier functions, which you know is orthogonal to all the others on the given interval, and then you just do the integral, and the only thing that's left is the coefficient of your function's expansion in the basis of these Fourier functions. Okay, so that's the idea. Orthogonal functions, orthogonal polynomials, and things like that, they all work according to this logic. They are orthogonal to each other, meaning that you can take a generic thing and kind of magically slice out just the coefficient of that one. Okay? I'm sorry? So that depends on your boundary conditions. So here, indeed, in the so you mean here, for example, I kind of say, oh, let me put the minus sign on the x rather than the y, right? That's kind of what you're asking. So indeed, at the beginning, you might do that, and then you would write essentially the sine and cosine for the x and the exponentials here for the y. So this would work. But what you would find is that so because you're kind of computing the coefficients, if you're taking the second derivative, you're going to fish out the coefficients here. But then you're not going to be able to fit your boundary conditions. For example, the condition we had that the potential would vanish when we go to x plus infinity, that you cannot get out of the sine and cosine. These things are just like uniformly averaging to some zero value, but they're non-zero themselves at infinity. So then you wouldn't be able to fit your thing. So in principle, the solution to this problem here contains both for x and both for y these sine, cos, exponential growing, exponential decreasing. But just the boundary conditions slice this out to a subset of those. Okay, so you just have to check. Once again, I like that question because once again, it emphasizes what we are actually doing when we do separation of variables. We are throwing the kitchen sink at the thing and seeing whether something works. And if it doesn't work, then we go to the living room and we take the stereo and we throw it at it, whatever we can find until we find something that works. So if you throw something at it and it doesn't work, don't feel bad about it. Yeah, there are plenty of other things to try. And at some point, one of these things will work. Okay, so again, it's not constructive. It's really like attempts, trials, until you hit something that works. And then, because of your friend Green, you know that if it works, you found the solution to it. Okay? Is that clear, actually? So, yeah? Okay. So that's it for that. Okay.